Hello everyone, so I keep implementing the game of Go as it has been described in the Byte magazine for April 1981 by Xiangqi and Millen. And here I have a screenshot of the original program running on an unexpanded QM1. And this must be a picture of the terminal. Not a terminal emulator like we have these days, but a real terminal. I'm not sure which module is this, but anyway, it looks super cool. So, what do we need to have to make it look authentic? So we need our columns 0, 1, 2, 3, 4, 5, 6, and up to F. Same with rows. So the coordinates would be like used this lattice, like used to represent digits and lattice, used to represent the coordinates. Say 5, 5. The stone should go here, etc. So I would now show you the listings that I came up with, and then I will run the paper tape that I've already created in a QM1 emulator to show you how this looks and how we can place some stones on board and print them. This is quite cool. So this is the listing of the program that I have so far. So the most interesting and most exciting thing about this is that I was writing assembly code with a pen on paper. Then I was doing hand assembling. So these values, I did hand assembling to came up with these values. I'm not using any assembler or any other automated tools. So I'm doing the old school 6502 programming when you just create the code with a pen and paper. Then you input these opcodes into the computer. So in my case, this is the QM1 emulator for Linux that I've created recently. And then I just run it and it works. So after I checked everything out, after the version that is available on a piece of paper essentially works properly, and I'm assured of that, I then create this listing. So essentially, I type what I have on my paper to the text editor to come up with this sort of a structured representation. And then to make sure that I didn't mess up with addressing, with instructions, with opcodes, I put every single opcode to the memory by hands. Yeah, that takes time, but that's very exciting, to be very honest, So let's have a look how this works. Then I'll walk through the source code and we'll point out some places where it can be optimized. So currently we have 117 bytes for the single print board function, which is a bit of an overkill, I believe. I think this might be done much smaller, but a few words about this will be coming later. So this is the paper tape. You can create paper tape using the QM1 ROM, okay? And that's the way how I did it. So my emulator duplicates the output to the serial port, well, LCD screen essentially, when I'm asking it to create a paper tape, so I can naturally obtain this kind of file. And then I can load this file back. So I'm going to the emulator. So currently at location 0200 there is nothing, and 0300, this is where I'm supposed to be calling my function, there is nothing as well. So I just do L, which stands for load, and now it's waiting for an input, and I just need to copy and paste. It prints scheme by the end, which means that there is no error. It would print error otherwise. Now at 0200, I have the opcodes. Essentially, I have these opcodes. So 0200 and these codes 0203 and this code 020B, 020B, 08, 19, 12, then 020C, this would be 20, print whatever we have in the A register, print the space, etc., etc. So all the opcodes are here. Yeah, so I've been doing this manually. Okay, don't scroll in the terminal. And if we go to 0300, so this is the function call, so 20 jump to some routine, which is available at 0200 hexadecimal. So go there and I press G, then suddenly I have my board being printed, and this looks really cool, isn't it? It really looks like the original, so exactly the same layout. Now, to make it a little bit more exciting, let's add some stones. We want so this at the moment this is zero index space. So 0 0 would print a stone here. So let's try to go to memory to board. Yeah, I forgot to mention that board occupies locations from 0000 to 00EE. The way how the offboard edges, like how the offboard squares are being treated, how to find offboard squares has been described in the previous video. Okay, and also another variable stones is where I store the ASCII representations for the empty square, for black stone, and for white stone. But anyway, if I go to 0000 and I say I do 01, this means black stone, and period to put this into memory. Now we have 01 in 0000. So if I print the board again, then here should appear the hash symbol, which means that we put a stone there. And let's try. And indeed, we have a stone here. Yeah, the only problem that I don't quite understand is why do I have X? Yeah, probably I did mess up with this, with the paper tape. So let me quickly check this out. So 0 to 72, 0 to 72 to E58. Yeah, 58 is the value of X. This should be 23, the value of hash. And yeah, a bit of mistake already. Yeah, it should be like this. It should be a hash symbol. I just messed up a little bit. But anyway, it doesn't matter that much really. So essentially X's are also look good. Okay, let's try to put the stone, say, on 5 5. So it would be 0 1 2 3 4, 0 1 2 3 4. So hexadecimal 4 4, and let's put 0 2, which is the white stone, and print. Yeah, and we have the white stone here. Yeah, looks really cool. And we can put the stone wherever. At the moment, no the tracking of groups is working, so stones would not be captured. So this is just a bare printboard function without pretty much anything else but this. And yeah, it does essentially what it has to do. It just represents the internal state of the board. So once this is clear, I want to emphasize some co-related stuff, because from the user perspective, yeah, this is quite trivial, not really interesting to have a look. In Python, you can do this like in a couple lines of code, much easier, but it's not about the result. It's about the optimization of the code, of how you represent the logic using the bare opcodes, essentially. So let's go back to the source code. So this is the most interesting part, at least for me. I want to point out those places within the source code that I think are really far from being optimal, and there is a room for the further improvement. So the first thing, so in order to print these this notation, so when we load the values from 0 to F into the A register, and then we try to print this out. Before this, we add 30, which is the ASCII value of 0 to represent this. And then we need to add the ASCII value of A to represent the letters. And this results some annoying branching in the code. So for instance, we ask whether the X register is the counter, whether it contains hexadecimal A, which is the decimal 10, and in case if it's greater or equals than that, in case if it's less equals than that, then we want to add the digit, and we branch to here. And otherwise, we want to add the character, and then we branch here. So this like creates branching, which probably could be avoided, especially bearing in mind the fact that when it comes to printing rows, although the code is not absolutely similar, but still we have we have this logic here, and again branching. So it's sort of a duplication already, and then printing the row. So really lots of code is spent, lots of bytes has been spent to this print. Okay, so one of the optimization that comes into my mind is maybe we could use, since we have some spare space in the zero page, we could potentially create a string representing the values, the string value, the character values, yeah, ASCII character codes for 0, 1, 2, 3, 4, 5, 6, and up to F, and then just create a simple print string function that essentially would be outputting the string. That's one approach, and we cannot output the string when it comes to the vertical representation. But again, I think that maybe if we can just print a single character. So it's not exactly print string, but yeah, the loop would be a bit different. But I think this generally takes less bytes to come up with exactly the same result. Another problem that currently off-board squares that we encounter. So we do like ignore the off-board squares. So you see, like it goes from 0, 0. So this is the address. So this is the absolute address of 0, 0, 0, 0, 0, 0, 0, 1. So this is the zero page essentially. Starting from 0, 0 ends up with 0, 0, EE. Okay. And when we go here, and then we encounter the 0E, and the next one is 0F. And like I have been explaining in the previous video, so once we have F, letter F in the left nibble of the byte or in the right nibble of the byte, we treat that as an off-board square, and the code logic represents that. So essentially, we comparing with the EF, which cuts all the values that starts with F0, F1, F2, etc. And also to get rid of off-board squares on the right-hand side and also on the left-hand side, because if we go in left here, then we encounter this one. So we start with this one, go in left, and then we encounter this one. So essentially not this one, but here would be the off-board square. So we know that it's not going anywhere. So off-board square, we skip it. Same if we go from here, say, to here. So the value here would contain F in the leftmost nibble. If we are here, we go into the right. In the rightmost nibble, we would have F. Same if we are here and we go to the left. Again, here we encounter the value of the index with containing F, so essentially 5F. We know that is off board. But the problem with this approach is that the very first time we encounter a new line would be after the first line. So we just print this one, then we encounter the off-board square, and once we encounter an off-board square, we go to print a new line. So this is the code that is responsible to. So this finds the off-board squares like this line gets print with these two lines, and all this entire column gets print using these two lines. And in the case if we encounter this particular one, so if we know that we are here, then we want to print the new line, right? And here we branch to like printing the new line. But the problem with this approach is that so we come here, then we print the new line, and say every time we print the new line, we also want to print say we encounter a new line. So we go here, we go off board, the new line. So then we go here. So not just printing the new line, but we also want to print the row number, okay? But with this approach, we need some additional code to print this row number, which is not very great because it just takes more code. So this is exactly what's happening in the code, which makes it messy and ugly. So when it comes to printing the row, essentially, let me find this. I'm not quite sure exactly. printing new line. So this is the initial new line that we print. No, hold on a sec. Not like this. So the loop. So this loop goes to print the position. This already goes to return. Yeah, I'm wondering where do I just want to say that the place in the code where I print this is separate from all the rest. I just try to find this. Okay, I guess this is it. So yeah, before printing the position, before starting this loop, this is the loop to print the position. This is it. So this is the only amount of code that is needed to print this entire board. So like the smallest part makes the biggest part that we want to see on screen appearing on screen. But I have this ugly part here, which essentially prints the number of 1. It prints 1 before we start the routine to print the entire board. And this looks really ugly. If we had a different logic, if the new line occurred starting from the very first line, in this case, printing this 1 would be the matter of following this routine, particular where we print all the rows. Okay, so this new line just prints the. So we need to preserve the value of X register because the jump routine to print the new line affects the X register. So we then need to pull this back and restore. And essentially, yeah, here, so we either add the digit or characters to the same code, the same duplication as it was here. Yeah, but the problem is that this code works only after we encounter the first empty square here, so starting from this one. And we have this ugly addition of up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bytes, 13 redundant bytes. So if we somehow could have the new line before the row, in this case, I think we could get rid of this piece of code. And also, if we combine this with an idea of having a ASCII character representation for the 0 to F, this coordinates. In this case, we don't need this ugly branching here, as well as this ugly branching in here. And this can significantly simplify the code and reduce the code size. So the way how I think how this can be done, so essentially we have zeros in the rightmost nibble for this row and zeros in the leftmost nibble for this column. And if we track the offboard squares using these, then on the one hand, 1, 1 becomes real 1, 1. Okay, so this might be a hint really from... So this picture might be a hint that essentially the real 1, 1 is the actual 1, 1 point, which I didn't quite think about earlier. Yeah, in this case, we do encounter this new line label at start. So say we loop starting with the 0, 0. So we already have the new line being printed. Also, we don't need this additional new line being printed before the printboard function, so we can strip this as well. Yeah, I think this might significantly reduce the size of this assembled version, really. The only question I have here is, let's say we encounter the very last one. Yeah, then we probably need to add one last new line after we are done with the board printing. Yeah, probably. So probably this line would still go. But in this case, we don't really need to preserve the X register. Okay, we didn't preserve the X register here as well. But yeah, so I just want to give you an idea, guys, that you know, if this was like the regular programming project that I had like tons of in the past, I wouldn't even be thinking about this. I would say like, okay, I have the board printed, I have the off-board squares being detected properly. So what else can I be ever dreaming of? But when you write in 6502 assembly and do hand assembly into 6502 opcodes, then when you see how ugly it looks, it really brings a desire to make it better. For some unknown reason, I don't know why is that happening. So usually, like normal programmers, when they write in high level languages, they also like may not like their code and try to make it better, improving the code all the time. So working with the code is a general consideration for programmers. But for some unknown reason, for me, I don't know why. Like when I do some freelance jobs, I don't care about code much. I care about the income that I get for the job getting done. So I just pay my attention towards getting the job done properly so that my script does exactly what it has to do. Then I get paid, everyone is happy, and I don't care how the code looks because I have more important things in my life to care about. But when it comes to 6502 programming and machine codes like this, for some unknown reason, I really feel this strong desire to keep optimizing the code. And like, if this was a high level language based project, I would have gone through the rest of the functionalities. I would have already been implementing the next routine, like count routine to count the liberties of the connected group on a Go board. But now I really have a strong desire to optimize this routine. And despite the fact I've spent like a few days to come up with this code, and again, all this was written by hand. Yeah, I still like have a very strong desire to essentially optimize it and make it like much smaller, at least twice smaller. So essentially, I don't know. I mean, like print position. Yeah. So essentially, this is the most critical part. So this part prints the entire board with a stone representation, right? So the rest of the code, so this ugly stuff here, as well as this ugly stuff here, it's all just to print the coordinates. So how can it be that the code that is required to print the coordinates is almost twice as big as the code to print the actual board? So this is not right, yeah? So when I do, like, finally, I just want to give a conclusion that I came up with. So the reason why I enjoy coding in 6502 assembly and manually hand assembly this to opcodes is because I can entirely focus on the code itself, try to make it smaller and look better. So I don't care much about the functionality here. I'm not in a hurry to make it work in as fast as possible because I've implemented this in Python already, so I know that it works. I know how exactly we'll be playing Go. I don't care much about that, really. I know the result already up front. But trying to make the code really like small, nice, cute, and optimized for size is probably my prior goal. And I feel big, like real pleasure when this is happening. So I enjoy doing this exact work and optimizing these tiny little up codes. So yeah, guys, this is from my side. Thanks for watching. I'll see you in the next video. Until then, and cheers.